Anyway, let's come back to this Nobel Prize over here. Just to give you a perspective what the power of that technology means. You know, if you have AI that would be fed by data about our thinking, feeling, and what we do, and that would be done on a global scale to basically manage the world affairs. Just imagine how far we could go. Like now we have ChatGPT, creates text, actually pretty good text, I would say in many cases. And it has been fed by, let's say, all the texts that were out there on the internet, okay? Now, the next thing is, of course, you feed it with all the pictures as well, and then all the movies, and then all the Internet of Things data, and all the nanotechnology data that I've been talking about just before. And then you could create basically a machine that would produce not only the next sentence or the next paragraph or the next page of a text or in the next movie, but it would literally be able to create our future. It would be a history machine in a sense. It would be writing history. The question is, how much influence would we have ourselves on that future? That would be eventually our history. Now the question is, would that be the best of all worlds? And that's, of course, the goal. You know, the people who build these systems, let's assume they're not bad people. They want the best for everyone. So they want to optimize the world with all the data, figure out what's the best version of the world and how can we make it happen. That's the idea, okay? Question is, how good is this idea really? And then, of course, everything depends a lot on how well can you actually fit reality, because that's the model that you use in order to create the future, right? And if we believe Geoffrey Hinton's work and others, then basically it suggests that we should not be afraid of too many parameters. You know, just the more parameters, the better, basically. That's the idea. And that encourages black box algorithms, right? So we would be represented by black boxes that are being fed by surveillance data, and eventually those black boxes would look more and more similar to us and behave more and more similar to us. And so the question is, could society be run like a giant machine? I want to look into one detail. Well, first of all, let's assume it would be something like a machine, you know, something that can be run like a very complex clock or whatever, you know. So there's these parts, and those parts would perhaps be people, and those people would interact with each other, and those interactions would have to be well represented, of course, by that model if it wants to be right about the best of our futures, right? So it needs to figure out how do these parts interact. And then you want to influence it, right? So you want to drive that system. And then really it depends on, is that interaction this way or is the interaction that way? And if you get that wrong, then bad things will happen. And there are many different parts of the system that you need to fit well if the outcome should be good. Okay? I can imagine sometimes things will go wrong. But the question is, how often will that happen and how bad will the outcome be? Let's look into calibration, okay? And I've here used an example that has been worked out by probably many people, in particular by my postdoc, Dino Carpentras. And So he has plotted basically a parabola to the power of 2 plus some noise. So it uses a random number generator to get those points over here. Okay, you can do that. Everyone can do that. Okay, then the question is, what if we fit this parabola? We don't know if we get those data points that there's a parabola of a power 2 behind all that. So then the question is, say we would fit with polynomials of degree 2, 8, or 15. What do you think will be the best fit? So we have applied a least square method, and we get an error of 13 for a polynomial of degree 2. That would be kind of the right class of functions, right? Turns out, however, the polynomial of degree 8 has an error of 11 only, and the polynomial of degree 15 an error of 10. So that's the best fit among those functions, okay? Now the question is, how meaningful is that? So what we'll do is we'll produce again a data set the same way with different random numbers. And this is the data set, okay? And now we will use the fits that we've created before in order to predict that data set and calculate the deviation between the prediction and that data set. And that's called validation. And it turns out, okay, now the polynomial of degree 8 has a much bigger error of 53. And the polynomial of degree 15 has an enormous error of 75,980. So this is the problem, like in order to have a good fit, more parameters are better. We know that since decades. Every social scientist learns that probably in the first semester, and that we should care about how much is the explanatory power of a parameter. And so more parameters can mess up their prediction power, as we've seen. And now today's models, as you know, have billions, if not trillions of parameters. I don't know what the military models can do, but probably even more parameters, which according to this would not necessarily make everything better. And what are the implications? So what we do as we fit the world by an AI model is we create a lookalike, a highly realistic lookalike, where we would have difficulties telling the differences between reality and a digital twin. But still, it's not the same. And so there could be really errors, there could be disinformation, and that could be meaningful and could create bad outcomes. And we have a very nice word for that. It's called hallucinations. It may look even artful, but it could mean that people die. Let's be honest about it. Okay, so basically, it's really important that we have to take into account confidence intervals. We cannot exactly measure or fit a parameter. There's always some uncertainty, and that uncertainty has implications. And in order to figure out the implications of that, one should do a sensitivity analysis. But doing that sensitivity analysis for 1 trillion parameters will basically make you busy for, I guess, 100,000 lifetimes or so. So it's not doable. So it's not being done. And that's why I've said a couple of years back, society is not a machine. And we should not treat it by optimization and control. It's a living being in a sense. It's as we will see, it's a complex dynamical system, and that has important implications. Okay, and in fact, there have been many attempts to make cities smart, but also to increase livability, the quality of life by this, and that has not always succeeded so well. So many of the evaluations that I know of are pretty disappointing somehow. I wish myself it was different, but we need to understand that a society, life, a human brain, the immune system or an ecosystem are different kind of systems. These are complex dynamical systems. Now, as you know, in the beginning of big data, Google's Trends was one of the big success stories, right? So the idea was we could nowcast. We could see how many people are ill because they're Googling for, oh, I have a headache, what should I do? You know, I have a fever, what does it mean? And all this kind of things, and you can extrapolate that basically and figure out how many people are likely to have a flu. That worked pretty well until they violated one of the fundamental things of science, which is you should never change a system while you measure. Because, and in particular, what they did is they were trying to influence the behavior of people to buy medicine, for example. And this way they have changed the system as they were measuring. So the measurement was wrong and they had to turn it off. Okay. We need to understand data science is a reductionist approach, but there are complex dynamical systems out there. And there are many reasons why the black box approach has limitations, measurement errors, sample biases, classification errors, correlations are not causality, overfitting, perhaps conversions may be not happening, models may not be robust, they may be sensitive to parameter changes, context may matter, ambiguities may be there, computational limits, halting problem, undecidability, and finally, complex dynamical systems. And that's what I want to focus on now. You all know the game of life, right? It's based on 3 simple rules. Produces funny outcomes, looks pretty unpredictable, at least to some extent. And you can use this data to feed it into an AI system. And of course, it will approximate that dynamics. But it will not give you the 3 rules that produced this dynamics. So figuring out those 3 simple rules is a very complicated problem that many AI systems would not be managing to solve. So we want to look into complex dynamical systems. What you see here is a couple of different realizations of the same set of equations where we just change parameters a little bit, and you see the outcomes look quite different, okay? Complex dynamical systems are known to us from turbulent fluids, traffic flows, large supply chains, social, political, economic, and ecological systems, financial markets, group dynamics, crowd behavior. And we know that there are limits of predictability, right? We can forecast the weather with some accuracy, but we cannot do that over a month or a year or 100 years. And even if we would have a million times more data, that fact would not fundamentally change. Why can I say that? Because we know the reason for this. And there's a physical theory called turbulence that tells us that in a turbulent system, and that matters for weather, little changes can have, if you just wait long enough, large effects. So your system would change in unpredictable ways, would behave largely different. And a very similar phenomenon is known from deterministic chaos. And there's the butterfly effect that is trying to make understandable something that is really hard to believe, I should say. That if, under the right conditions, of course, if a butterfly would flap its wings, that could change the world. Not tomorrow, but if you wait long enough, it could change the weather, it could change whatever. Hard to say. So little changes could have huge effects. And that's related to the sensitivity I was talking about before. And of course, there are people who've been thinking about chaos control, right? Here is an example, and you can see over here that if you try to control the chaos on the left, it's controllable, yes, but actually the outcome on average is worse. So controlling chaos will not always give you the better result. Well, now let's go back to this idea of the control room to control the world. Like let's assume there would be so many buttons to change things in this world and repair it, make it well behaved, I know there are many politicians who dream to have such a thing also for politics, and also people running universities who have this dream that there would be a button, an incentive system to push up the number of publications or the number of review papers or number of students being taken care of, or the number of review papers or number of media reports, or so would that work? Let's try with one button, okay? Let's have a look at the Lotka-Volterra system. It's a model for a very simple ecological system, predator-prey equations, as we call them, foxes and rabbits. And you see their expected oscillations in the population size. Now, let's assume that there is an optimal ecological equilibrium, and it would be this point. And in order to get there, there's a hunter who's trying to push towards this point, x1 naught, x2 naught. And as the hunter is doing that, the system actually goes somewhere very different. It goes there, not there. Of course, there are systems where kind of pushing for that equilibrium would work, but there are also these kind of systems, and there are more of these kind of systems than most people think. Okay, so there is an illusion of control. Just take this example, right? It's so simple to drive in a circle and not have an accident. Nobody wants to stand still to produce a traffic jam, but this is exactly what they're doing, unintentionally so. The reason is systemic instability. Little variations amplify, and that is what causes the stop-and-go traffic. There is a solution we have developed together with a car company some time back. And that solution, however, is not based on centralized control of every car. We've started simulating the stop-and-go traffic. So you see, we understand the phenomenon. We can produce it in a computer. I've done that many years ago. And so we've been working on autonomous driving at that time, also quite a few years ago already. And we will take a helicopter now because we're really angry about this traffic congestion. And now we see there's a little on-ramp where cars are trying to get on the freeway, and it produces little disruptions, and those disruptions amplify and cause the stop-and-go traffic. We'll now shortly turn on a traffic assistance system where cars will autonomously accelerate and decelerate. And now it's turned on. Based on measurements of a laser sensor or a radar sensor. So cars determine distance and relative velocity. Actually, it's enough if 30% of those cars do that. So as you see, we get rid of the traffic jam. Even though there's the same number of cars going into the freeway and the on-ramp, the traffic congestion goes away because we have changed the interactions between the cars a little bit. And by self-organization, another outcome than the stop-and-go traffic flow occurs now, which is the free flow. And what we have to do is we have to find the right kind of interaction mechanism, and this is called mechanism design, okay? So the success principle is not centralized optimization and control here, but real-time data measurement and real-time feedback. That does all the trick, you know. It does the job like magic for us if we just understand the system and use the properties of that system for us. Now, it's really important to understand complex dynamical systems. We often focus on the components of the system. It could be people, it could be cars, it could be companies, it could be buildings. And we would instinctively believe that the properties of all those components determine the properties of the system. And that is true only to some extent. Because when we have interactions between those components, then they would change each other's behaviors. And if you just have enough interactions, and if they're strong enough, they would dominate the behavior of the system. That means the properties of the components would be less important or not important. The properties of the interactions would be important to understand what happens. That means what we don't see is what really matters. As we go on networking the world, we need to focus more on those things we don't see. Those systems change their behavior, and often would we not see the intended effect. We would see side effects, we would see feedback effects, we would see cascading effects. And here is a little movie illustrating that very nicely, a suitable experiment for a rainy weekend, I would say. I can see one local perturbation can eventually mess up the entire system. And we have these kind of phenomena also in reality, like in financial systems where we had bankruptcy cascades. What we also need to consider is that there's a problem of dark data. And it means that data volume grows faster than processing power. I mean, we cannot process all the data that's being produced in the world. And there's more and more dark data. And plus, as we network the world, complexity of the system grows ever faster even than data volume. And even though we have the best technology ever and more data than ever, it seems like we're losing control, paradoxically. And so we need a new control approach, not top-down centralized control, but bottom-up self-organization that we can assist in digital ways. And that's the approach that I recommend. So we were inspired very much by this example over here. I recorded that in Egypt. I see it's a highly diverse traffic, kind of pedestrians, cars, buses, lorries, donkeys, horses, whatever you can imagine. And it just works. I mean, there's some noise, I must admit that, could be replaced by Internet of Things sensors, but it's a design that makes it work. We have unidirectional flow in the front, we have the opposite unidirectional flow in the back, and we have a little buffer in the middle, which really is important to allow everyone to adjust the speed in such a way that you would find a gap when you need it. If you don't have the separation of the two opposite flows by the buffer, then it will never work. So we can design for self-organization. And we have tried to do that for traffic flows in cities. What we've observed for pedestrians is that at bottlenecks, there are oscillatory flows, and it looks like there is a traffic light, we're calling this, but in fact, there's not. And we have basically transferred this principle to control traffic lights. And you see the pressure principle that we have formulated produces self-organized green waves. And what we do is we measure the outflows from road stations, but also the inflows in order to anticipate how many cars would we have to serve in order to avoid that cars would be unnecessarily stopped. Now, we have compared 3 different approaches to control traffic lights. The control center that tries to get as much data as possible from all over the city, and then trying to come up with an optimal control and impose it on the entire city, like a K-nobody indicator. Now, most people would think that should be the best. Then in the middle, we have looked at a homo economicus approach. Each intersection separately tries to minimize travel times, considering the cars from the neighboring road stations, and nothing else. Doesn't care about the rest of the city. The selfish. And here we do the same thing, just that large queues will be cleared before we go back to the travel time minimization. And so it's not a regarding because it helps the neighboring intersections to avoid spillover effects. It's friendly. We would expect the left solution is the best, the middle one the second best, and the third on the right the worst. Let's see what really happens. For centralized control, we get the red line. Queue length increases with capacity utilization, traffic volume, if you wish. And that's what we expect, okay? Now, for the homo economicus approach, you get this violet dashed line. And you see it's much better for low traffic volume. But then it gets out of control. However, the third approach, surprisingly, is better all the way. So we can make the invisible hand work. We can have bottom-up self-organization, outsmart optimal top-down control. Why that? Because traffic light optimization is NP hard. You cannot go through all possible solutions in real time. You need to make simplifications. You need to come up with the optimal control offline and apply it to a typical situation, which is, however, never there. We instead adapt flexibly to the actual traffic situation. It's not 100% perfect, never, but say 90% perfect all the time regarding real traffic flows rather than 100% perfect for a situation that does not occur. Okay, how well does it work? Much better performance, actually. Surprisingly good gains in performance. And you can see here quite clearly, if you compare what they had before, the green wave even that they had before, and the self-organized green waves with the approach that we developed, you see this big difference. There's a lot less red, that means a lot less waiting. And so it works much better, by the way, for everyone, for cars, for buses, for pedestrians and cyclists. And now you may ask, is AI going to outpace this? Is it going to be better than this? This is based on an analytical formula. It's not easy to derive, really. It requires a lot of thinking. And so we have compared that. So we had a machine learning student who loves machine learning, you know, and then he still compared with our analytic approach. I see the analytic approach actually was doing best, not necessarily much better, but see what happens if we have a disrupted system. That means if we have building sites, if we have accidents, those things that do happen every day, but are not part of the plans. And so the machine learning has to learn for that again, right? It's a new situation. The analytic plus does not have to learn. Analytic plus is much better, it turns out, than machine learning. We even tried pre-learning. Pre-learning makes, of course, machine learning solutions much better than without pre-learning, but still, it seems like there are problems out in the world, perhaps that can be better solved with not black box machine learning. And this is, I think, an important insight to have. So I want to conclude now. Oh. Of course, now everyone's fascinated. A Nobel Prize, you know, we should do the same thing, and then, you know, we'll get the Nature paper published and a science paper and all of this. But, you know, still, don't lose your mind, okay? We as scientists need to stay reflective, critical, both in good and bad ways. You know, we have to see the shadows as well as the light of those solutions. And he himself has warned of dangers to humanity. So that means that we should spend some thinking on that. Because there are actually some examples of Nobel Prizes where things went wrong. Yeah, just to give you some examples, like Nobel Prize in 1997 for economics, Black-Scholes theory. You know, wonderful theory. It was then implemented in the so-called long-term capital fund. And made a lot of money until it crashed the markets and almost the entire world got bust. You know, the financial system almost crashed. Then Peace Prize for Barack Obama, you know, he got it, then he started the presidency, then several wars started. So did not work out as expected. Some people also saying same thing with the nudging-oriented Nobel Prize of Richard Thaler. You know, this is one of those insights that's being used to manipulate our feelings and our behavior. And some people think it's a psychological abuse if you do it the wrong way. So yes, I want you to keep working on better versions of our world, but not necessarily based on this attempt to come up with the one optimal solution that will never occur, okay? And with this, I'd like to thank you very much for your interest.